centimeter chord and the first harmonic is formed. What is the frequency of the note played? So what's the wavelength here? 60 centimeters. And frequency equals V over lambda. So it's 340 over 0.6. 340 over 0.6 is... the ugly one indeed. 567 hertz. So if you can write that down as the first answer. Right, number 2. What is happening in number 2? Some wind blows through an open at both ends 40 centimeters pipe. What is the fundamental frequency? So do you remember for this pipe on the diagram it goes up in half? So for the first for the first harmonic, it's half a wavelength. Isn't that what we had in the picture?
What was it? Was 500?
No, listen.
The previous question.
Yes, 566.
567 hertz. No?
Yes.
Yes. 567.
Okay,
Yes.
And,
So what's the length of the pipe for number 2? Length of the pipe in number 2? 40 centimeters. Is it 4 or is it times 2? 2, because this is an open at both ends pipe. They go up in half wavelengths. No, that's closed at one end, goes up in quarters. Do you know what I'm saying? Are you sure? So if it's a 40 centimeter pipe at the first harmonic, then half a wave is inside of it. So what is the wavelength in total then? 80, yeah. Because from the pictures I gave you earlier, it's like this. Come on, mouse. Son of a blank. There we go. Right, so when it was open at both ends, the fundamental was like this. Like this and like this. Half a wave's in it. So the wavelength will be twice 40 centimeters, that's 0.8. And what was I looking for? The frequency? Frequency equals V over lambda. 340 over 0.8 is 425 hertz. Right, that was number 2. Number 3. Got that, Andrew? Number 3. A closed end organ pipe is used to produce musical notes. The third harmonic is formed at 1100 and the fifth is at what frequency?
At one end and open at
Closed end organ pipe. Yeah, closed at one end and open at the other. So the third harmonic, if it's closed at one end, they go up in quarters.
Yeah.
So the third harmonic has how much of a wave? 3 over 4 of the wave is in the length of the pipe. So it's 4/3 the length of the pipe. What's the length of the pipe? Do we know this? No, we don't know it actually.
So you need to calculate frequency and speed and to find the
Yeah, because we know that V lambda is V over F equals 4 over 3. Now actually we know the frequency and the V, don't we? It's 340 over 1100 equals 4 over 3 lambda. Is this what you did? Lambda is 3/4 of that number.
But then didn't you say that lambda, it's a full lambda in the formula, or is it?
No, I just rearranged it. This is what I said.
Isn't it?
This is what I said. True or false? 3/4 of the wavelength is the length of the pipe. 3/4 of the wave is in the pipe. So that means the wavelength is 4/3 the length of the pipe. I just rearranged this, yeah? Or no? 0.75 times the pipe is that long, 0.23. Anyway, that's not what we want. We want, what was it we wanted? The frequency of the fifth harmonic. So the fifth harmonic, how much of the wave is in the fifth harmonic? 5 quarters. So 5 quarters of the wave is equal to the length of the pipe, which we now know the length of the pipe. So the wavelength is equal to 4/5 the length of the pipe, which we know. I don't want the wavelength. What do I want? The frequency. So V over F is equal to 4/5 the length of the pipe. So the F is equal to 5 quarters the speed of sound over the length of the pipe, if I rearrange this. So if I just take this answer here, and I have 340 divided by this answer, multiplied by 5/4, 1833 hertz is the frequency of the fifth harmonic. This one's a bit trickier now. A bit trickier, for sure. What number was this? 3, wasn't it? Okay, 4. Do you write this down? 4. A woman is working with a large machine that has 2 settings, fast and slow. When on slow, the machine rotates at 240 times 1,000 revolutions per minute, and the machine sounds louder. She reasons this is because the standing wave is formed in her ear canal. Assume the first harmonic was formed in her ear. Estimate the length of her ear canal. So, her ear, open at both ends or close and open? Close and open. So the first harmonic, how much of a wave is in there? 1/4. So we know 1/4 of the wave is in the length of her ear. Okay. How can we get the length, the wavelength? Well, that's V over F. Do we know the V? Yes. Do we know the F? Kind of. We know it per minute. What was it per minute? 240,000 per minute. But we want it per second, so we just divide that by 60. So we have 1/4, 340 times 60 over, please type this in, 240,000, and that will be a number. "15 millimeters is the length of her ear canal." What was this for? So cute.
So small.
This is a typical size ear canal, ear canal. How deep your ear is.
Yeah, but like,
Wow.
I'm pretty sure I can put the cotton thingy deeper than 15 millimeters.
Don't please.
And red light was this
Sorry, what is it then?
0.02125.
Oh, I mistyped then. So not 15, but 21 millimeters. Okay, yeah, sorry, that sounds a bit more reasonable. Still, I wouldn't be putting things in your ear longer than 21 millimeters. It's not medically advised. And please remember that's the ear canal, so that does not really count the exterior part. It's the part of the ear where the wave is formed and causes the drum to vibrate. Yeah. Continuing. Next one. A car is traveling 120 kilometers an hour between 2 radio towers. The signal increases and decreases as the car travels between the towers, and they are 43 seconds apart. What is the frequency of the radio wave? So, interestingly, what is happening here, we have 2 radio towers, and they're both broadcasting a radio signal, but the result is a stationary wave has formed between them, and the effect is the signal, like what we did in class today of loud and quiet, the signal strength of the wave increases, decreases between the two towers, just like what happened in class today with the sound.
This can happen.
It can, but I think it's a bad design to have two radio towers broadcasting in such a way that part of your signal is destructively, happening. It can happen. I can't imagine anyone designing it in such a way that it would happen like this. I would hope not, because you're wasting energy by having the signal cancel here. But situations where this could happen, actually, maybe not two radio towers, maybe two Wi-Fi routers operating at the same frequency, causing areas of black spots in the house where the signal is weaker. So, okay, maybe not happening with radio towers, but certainly could happen if you have several Wi-Fi routers in your house.
Both of my parents are shouting at the same time.
Your father will be at a different frequency, a lower frequency to your mother, so it will be okay. All right. Let's have a look here. The car is traveling 120 kilometers an hour. Let's change that into meters per second. Yusuf, can you type in 120 times 1,000 divided by 3,600 meters per second? What's that? 33.3. Okay. Every 43 seconds you get one of these nodes or antinodes. So the distance between them would be 0.43 times the number on your calculator. What's that, please? Every 43 seconds. 14.3 meters. Yes. So every 14.3 meters you have this, sorry, what am I doing? It's not 0.43. 43 seconds is 43. So 43 times 30, it'll be, I was off by a factor of 10. 1,432 meters. So every 1.4 kilometers the signal dips. Okay? What is the wavelength here? If we have a stationary wave and we know the length between the antinodes. Double, very good. So the wavelength here is 2864 meters. And how can we get the frequency? Frequency equals C over lambda, 3 times 10 to the 8 over 2864. What is that, please?
Isn't this the wavelength of the first harmonic?
No, I don't know which harmonic it is, and I don't actually care, because if I know the distance between the antinodes, I know the wavelength. The only reason I need to know which harmonic it is to work out the wavelength. I don't care what the harmonic is. It will not be the first harmonic.
Yeah, but sorry, if we're doing this, doesn't it mean that we are only saying that this is forming one wavelength?
No. In my picture there are many waves.
Yes.
Yes? And I'm doing this now because I am saying the distance between these antinodes is 1432 meters. I do not care how many there are. I just need to know the length of one wave. If I know the distance between the antinodes, I can double it and get the length of one wave. If I knew the distance between the towers, I could divide by this to know how many wavelengths there are and thus work out the harmonic. But as I said 5 minutes ago, I do not care which harmonic it is, I just care for the wavelength. Cool? Cool. What is the frequency here? 104,749, which is 104.7 kilohertz, which is the frequency of the radio station. If you look at radio station frequencies, they are in kilohertz. This is FM 104 radio station. 0.7 here, yes.
We have a channel, .com, 104.8.
This is Dublin FM, if you're wondering. Okay, continue. Last one. In real life, there is an error when we try to estimate the wavelength inside of a pipe. This is because at the open end we said there's an antinode, but it's kind of a bit fuzzy. It's not a perfect antinode. So we have a small error when we try to calculate the wavelength. Here I say there's a standing wave of frequency 1100 in an open at one end pipe and a fifth harmonic at 1800. So let's write that down. The frequency is 1100 and the harmonic is the third. When the frequency is 1800, the harmonic is the fifth. So if you look at the first situation, you can say if it's a third harmonic, how much of the wave is in there? 3/4. So 3/4 of the wave is in the pipe at the fifth harmonic, at the third harmonic, and at the fifth harmonic, 5/4. Do we know the wavelength? No, but we know the frequency. So we can say L equals 3/4 V over F. L equals 3/4 V over F. So you're distracted me. L equals 3/4 V over F. L equals 5/4 V over F. Do we know the V's? Yes. Do we know the F's? Yes. Do we know the L's? Yes. But the L's should be the same here, but they're not, because there's a small error in both cases. So what we really need to say is, I know in the question I put the error on the lambda, but I think I'll put the error on the L. It doesn't really matter. It's the same thing basically. There's some error in measuring the length of the wave. So really we need to say the length of the pipe, which doesn't change, plus the error equals 3/4 340 over 1100. The length of the pipe plus or minus some error is equal to 5/4 340 over 1800. But because I have two equations, I have enough information here to work out the length of the pipe and the error. So, Yusuf, can you type this in? 0.23, thank you. And no, do you know what? I'm sorry, there is a mistake here. I should have put the error on the wavelength, I'm very sorry. So there should be here plus error, here plus error, here plus error, here plus error. Okay, so now I get L equals 3/4 times 340 over 1100 plus 3/4 the error. And here I get L equals 5/4 times 340 over 1800 plus 5/4 the error. What did you say this one was? 0.23?
Yeah,
3 plus 3/4 the error. And then what's this one here? L equals plus 5/4 the error.
2.36.
Oh no, they shouldn't be that different. 5 over 4 times 340 over 1800.
0.236.
236. And this one is 0.23 only. Yeah. Okay, so these are easily solved. Give me the calculator, and I solve them using the calculator, because you all know how to solve simultaneous equations. If I solve, you are looking for a punch, aren't you? Yes, you are.
Looking for a handsome girl.
Mode 51 1 0 minus 0.75 0.23 1 minus 1.25. Now, Faisal, you are distracting me. I cannot type this in. 1 minus 0.75 and 0.23 1 minus 1.25 0.236. When you solve this simultaneous system, you will get L equals 0.236 and the error is 0.22 0. 0.012 with a minus. So the length of the pipe is actually 23.6 centimetres, and the error was minus 1.2 centimetres. So in real life, when you try to calculate the lengths of waves by measuring the pipe, it doesn't perfectly match up. I know in my picture I said, 3/4 of the wave fits in the pipe, but there's actually a small error at the end. This error is called the correction term, and it's usually quite small. There is actually a formula to calculate the error that doesn't require you using simultaneous equations, but this formula is not in the course, and this formula, to calculate the error, you would need to know the radius of the pipe. It's the radius of the pipe that's actually causing the error. I don't know, has anybody ever seen that before when doing this in high school? Now, this question did come up a couple of years ago. The only way for us to do it is a simultaneous equation. We do not have the formula for the error in the formula book, and even if we did, we do not have the radius of the pipe, so we couldn't use it anyways. We need to have two situations for the pipe so that we can form a simultaneous of the length and the error. If they only told us one of the harmonics, we couldn't work out the error. We'd have to assume the error is 0 and just do it normally. So I know this one's a little bit tricky, but we'll get to practice some more when we do revision questions next week. Okie dokie. Enjoy your weekend.
So,
No, I will try to.